Good morning from Dhaka, Bangladesh. This is the 10th lecture of AS and A-level chemistry lecture series, which will deal chemical bonding and structure. In the 9th lecture, I talked about ionic bond and its properties. In that case, I say that to form ionic bond, we have to have electron transfer from the valence electron of the atoms concerned. And then we get ionic bond. I've discussed it in details. So is it the only way that we have bond in chemical compounds or molecules? Definitely not. Why not? Because only transfer of electron or gaining of electron, we cannot explain bonding. But if we take care of sharing of valence electrons, then we can see that we can also possibly explain other chemical bonding. You see, in nature, we do have different types of relations. And therefore, it is not only one type of relations in nature. Hence, also in chemical worlds, we do not have only one type of bond. We can explain few compounds with one type of bond, and then we have to go for next. Why? Because we will see that we cannot only transfer electrons. It takes to transfer electron a lot of energy, valence electron. Therefore, sharing of electrons can solve this problem. In this case, chemical bonding, which we call covalent bond, we will see that atoms concerned are sharing electrons between themselves. Here it is, I'm saying, sharing of valence electron of atoms. Okay, why it shares? It has a tendency to get noble gas electronic configuration. And therefore, this configuration is relatively low in energy. Hence, the all atoms tends to either by transfer of electron or by sharing of electron gets noble gas electronic configuration. I hope you do remember noble gases, that is helium, neon, argon, krypton, and their electronic configuration is the stable electronic configuration. So bonding between electrons is an attracted force which make the compounds or molecules. There we will see in the following diagram that how bonding is going on by sharing of electron. You see, this is a electronic configuration of fluorine atom. We can see there is one electron here, and the next fluorine atom has got the same electronic configuration. But if we do share these two electrons, it becomes a noble gas electronic configuration outer shell. So by sharing of electrons, we can form fluorine molecules. Sharing of electrons of fluorine atoms, we can form fluorine molecules. It's not only that we will form diatomic atomic molecules. We do have molecules having 3 atoms, 4 atoms, different kind of atoms, and they also share with themselves and form bonds. We take an example of chlorine atoms here. Similarly, as like fluorine, one of the electron of chlorine, this atom, and another of the electron of this atom share together and form, you see, here form a pair of electrons, which is shared by these 2 atoms, and that is what is covalent bond. We then represent this chlorine with a flash, another chlorine showing the bond between these 2 chlorine atoms. Well, it is not only that one pair of electron can share by both atoms. We can see later, even in these slides, also later slides, that there are 2 pairs of electrons sharing with 2 atoms and thereby forming bonds also. And if it is two pairs of electrons, for example, in oxygen, we get double bound in oxygen, and that is the stable configuration. And similarly, if we share three pairs of electrons of each atom of nitrogen, we get nitrogen molecules. In next slide, we will see the Lewis dot structure of nitrogen molecules and chlorine molecules, as well as oxygen molecules, showing how they form covalent bond. Here it is. This is a representation of Lewis dot structure, which we showed in the last lecture. We said that we have to get the valence electron of nitrogen, and then around this nitrogen electron, we can share the hydrogen atoms, three hydrogen atoms, forming a ammonia molecules. Here is ammonia. So these bond between nitrogen, nitrogen, nitrogen and hydrogen, nitrogen, hydrogen, these are covalent bonds. But please note that we have, after doing this, we have a lone pair of nitrogen here still exist. Similarly, if we go for water molecules, we can see here oxygen has got the Lewis structure, and then hydrogen atom has all hydrogen atom has got one electron, and they share this electron with one of the oxygen of electron of oxygen, and thereby forming an oxygen and hydrogen bond. Note that we have two pairs of lone pairs of electrons around nitrogen, around oxygen. So here is a representation of bonding in water, leaving two lone pairs here, two lone pairs. Go for, let's say, this is a ethane molecule, ethane. So we have two carbon atoms and 6 hydrogen atoms. If we do like this, we will see that all here are sharing electron, one pair of sharing electron. And there we do not have any lone pair. Why I'm talking about lone pair of electron? When we go for shapes of molecule, we will see that we need this lone pair of electrons to consider and predict the shape. I said that we could have two pair of electrons, three pair of electrons sharing with each other, and therefore forming double bond, triple bond, etc. Here is the oxygen, which I talked earlier in earlier slide. The sharing of two pairs of electron here, two electrons from this atom, two electrons from this atom, and therefore sharing two pairs of electrons. And we represent it like this. I did not show the lone pair here. We do have two lone pair also, Here is the bonding in carbon dioxide. There are two pairs of oxygen and carbon electron, and here again two pairs of electron in carbon and oxygen, forming carbon dioxide. We know ethene, that is, it's a hydrocarbon. Here we can also see that these two carbon atoms are having two pairs of electrons with each other, thereby bonding, having two bond pair here, and then carbon and hydrogen having one bond pair, carbon and hydrogen having one pair, and therefore we show the structure like this. Well, you see, we have a symbolization here, dot and cross. This dot means the electron of this nitrogen, and cross means the electron of this nitrogen. So we are representing electron of two different atoms by two symbols, one by dot and one by cross. And therefore, here you can see the dot and cross means that one electron from here, a dot, one electron from this nitrogen atom, and thereby forming three pairs of electrons sharing here, and there are three bonds here. Similarly, we are going to ethyne. And we can see the same thing is going between carbon and carbon, and then carbon and hydrogen, carbon, hydrogen. And the representation, we do it like this. Just to show you how covalent bond is formed, that's what we explained here. In next slides, we'll see that not only this type of covalent bond is prevailing. In many compounds, we have also other type of covalent bonds, which we call coordinate bond or a dative covalent bond. That is what is coordinate bond or a dative covalent. What it is nothing but that it is sharing a pair of electrons, no doubt about it. But in that case, it is one atom is providing the pair and another atom is sharing simply. Other atoms do not give any electron to share. They just have a possibility to share the pair of electron of one atom and thereby forming bond. So in this case, what we have to have one atom with a lone pair of electron and another atom which has got unfilled orbitals. That means it has a possibilities to have a pair of electrons. One can donate and another can accept it, and then both share this pair of electrons. This is what is coordinate covalent bond. Here we show an example of coordinate covalent. You see, it is ammonia. I showed it, ammonia configuration. Do you remember I said that after forming a bond with hydrogen and forming a bond with hydrogen and then again bond with hydrogen, this is covalent bond. And then we have a lone pair of electron in hydrogen. This lone pair of electron can have a hydrogen ion where it has no electron, but it has got an unfilled orbital. And therefore, it shares with this lone pair, both hydrogen ion and nitrogen will share it, and forming ammonium ion like this. Here you can share it. And when we show this bond, what you see here, we showed an arrow here. That means the one having lone pair will have an arrow, and that atoms which will take this lone pair and share, the arrow will be like this, which the more electronegative atom has got lone pair. So from there, we have arrow to the atom which is having an unfilled orbitals. Yes, it is the way we can represent the ammonium ion Lewis dot cross structure and showing the bond, additive bond between this nitrogen and hydrogen. Same thing is there in aluminum trichloride. Two aluminum trichloride molecules. You can see this aluminum has got a vacant orbital here. This one has got a vacant orbital here. But this chlorine has got a lone pair. This chlorine has got a lone pair. So that two together will form a dimer, aluminium 2, chlorine 6, like this, forming a dative bonds. Here is a dative bond. Here is a dative bond. Other bonds are covalent bond. I hope I could explain this properly. Next, we go for sigma bond and pi bond. Well, now we are talking about sigma bond and pi bonds. Well, there often you get an exam. Are sigma bonds and pi bonds covalent bonds? Your answer to be given with the concept of sharing of electrons. And then you will see that yes, they are also covalent bonds, but they are named as sigma bonds and pi bonds. Why it is? You see, we are talking about electron clouds, which we call electron density. And we know that electron clouds are in s orbital, p orbitals, etc. So here we are talking about orbitals. In orbitals, we have electron density. And then this electron density have to share with one another and form bond. Is it? So sharing of electron means sharing of orbitals. Sharing more orbitals share with each other, then the resultant orbitals are called molecular orbitals. You are talking about only orbitals, p orbitals, s orbitals. We never talked about molecular orbitals. So when s orbital, p orbitals, they share with each other, then it becomes molecular orbitals, not atomic orbitals anymore. So the process of sharing these orbitals and getting molecular orbitals This process we call hybridization in chemical term, hybridizations. In next slides, we'll show how hybridization can occur. Mixing of s orbitals, here's the s orbitals, and one of the p orbitals. We know there are 3 p orbitals. One of the p orbitals, if we mix these two together, we get hybrid sp orbitals. The hybrid sp orbitals are 2 molecular orbitals. Similarly, if we go for 2 p orbitals and 1 s orbital, we get sp2 hybrid orbitals. In total, we have 3 molecular orbitals here. And if we take 3 p orbitals and 1 s orbitals, we get sp3 hybrid orbitals. And here we have 4 molecular orbitals, hybrid orbitals. We designate it as sp3 hybrid orbitals. It is possible also to form hybrid orbitals between s, p, and d, and call that sp-d hybrid orbitals. But that hybrid orbitals we need in d block elements chemistry, not here. Therefore, I didn't show these details here. I am talking about only sp, sp2, sp3 hybrid orbitals. And these all examples here will talk about sp, sp3, sp2 hybrid orbitals. So a few examples of pi bonds and sigma bonds are showing here. How pi bonds happen? You see, we have atomic orbitals, and therefore that can share each other in direction wise. So if it is head-on or end-on overlapping, head-on or end-on overlapping, that we call sigma bonds. Examples, you see, here is the s orbitals of hydrogen, and here is another s orbitals, another hydrogen atom, and when these two share, collide head-on, we get these molecular orbitals. And this is a sigma bond between hydrogen molecules. Okay, then this is head-on overlapping. How can we have another type of overlapping? We'll see in 3 dimensions that there is a possibilities of sidewise overlapping. And when it happens sidewise overlapping of orbitals, we call this pi bonds. And a few examples of this type of molecular orbitals in hydrogen, and then carbon-carbon, and carbon-hydrogen, carbon-hydrogen, hydrocarbons, and hydrogen cyanides. There are a few examples. What happens? Here we are showing 1 modified p orbitals and 1 s orbitals. When these two overlap head-on, we get this molecular orbital, which is called sp orbitals. And then these orbitals we call sigma bond. Okay. Similarly, we are having some example of sigma bonds here, carbon-carbon sigma bonds. And then we say we have p orbitals, and we do remember that p orbitals has got 3 directions. One is called px, another is py, another is pz. So when it is 2 p orbital in same direction, there is possibilities of head-on collision. But if it is in different direction, there is a possibilities of sidewise overlapping. And that sidewise overlapping gives us pi bond. And examples of hydrocarbon here. Yeah, you see, this is a carbon atom, and this is a carbon atom. And it has got orbitals, s orbitals, p orbitals. So this carbon atom and this carbon atoms has got a possibilities of a head-on overlapping and forming a sigma bond, carbon-carbon sigma bond. But then carbon and hydrogen atom, they also have head-on overlapping, and therefore they have sigma bond. They have sigma bond. But these two, these p orbitals and these p orbital of carbon atom, they are overlapping sidewise and thereby forming pi bond. Similar examples we can get in hydrogen cyanide. We'll see that there are 2 pi bonds and one, two. That is a sigma bond, and that is also a sigma bond, and then the 2 pi bonds here. two different sidewise overlappings happen here. And thereby we have sigma bonds, you see, has a pi bond, and we do have also sigma bonds between carbon and nitrogen. Okay, now we are coming to the next slide, and with this slide we'll finish the 10th lecture. You see, we have polarity in molecules, and that is what we have to count first. Electronegativity. We know electronegativity is the power of attraction of electron pair towards this nucleus. So this power, someone can have low power, someone has got high power, etc. And we say electronegativity has got a scale, Linus Pauling scale. And in elements in the periodic table, we have experimentally determined electronegativity for all elements. When the electronegativity difference is 0 for a molecule, we call that a non-polar covalent bond. If there is an electronegativity difference is there, and then we call it a polar covalent bond. We are showing here hydrogen's electronegativity is lower than that of chlorine electronegativity. So bond forming between these two, we call it polar covalent bond. If we take a hydrogen molecule, this electronegativity between two hydrogen atoms is 0. So therefore, hydrogen molecule has got covalent bond, which we call non-polar covalent bond. We'll continue this polar covalent bond and non-polar covalent bond in next lecture. Thank you very much for today's lecture.